Son of a gun. Welcome to Chapter 22 lecture. CHEM 2212. Quick review of free radical chlorination. A method to prepare various halogens, not very efficient. Also a review of electrophilic aromatic substitution as a way to prepare aromatic chlorides, bromides, and iodides, not to be confused with benzylic and allylic chlorination, which is again a different set of reagents, mainly chlorine and photons. And lastly, none of that to be confused with chlorine addition to an alkene, which makes a dihalide, and not on the board, but it is now. Addition to alkynes that make enes, and also tetrachloroalkanes. And the reason we're reviewing that right now is because in Chapter 22 we're going to see another type of chlorination called alpha chlorination. And Chapter 22 is also entitled Alpha Carbonyl Chemistry, and it's largely a culmination in organic chemistry, as many reactions in nature and thus physiology and biology use these condensation reactions to build up complex molecules and also break down complex molecules. And necessary fundamentals to understand the chapter include your functional groups, I know you know them, and also acidity. So organic molecules that are acidic would include carboxylic acids, sulfonic acids, and phenols. Those are by far and away our most acidic functional groups. And of course, none of those are as acidic as mineral acids like hydrochloric acid, sulfuric acid, or nitric acid. For synthetic purposes in the alpha carbonyl chemistry realm, we're talking about acidities much less, and due to the presence of hydrogens next to a carbonyl group. These so-called alpha hydrogens can be removed by bases, making nucleophilic species, and these nucleophilic species can be condensed onto other carbonyl compounds, or actually other or themselves, in what is termed self-condensation, to make a wide array of complex molecules. New functional groups that we're going to introduce include beta diketones, beta keto esters, and beta keto acids. These are particularly important as the alpha hydrogens in those new functional groups are not just alpha hydrogens, but they're doubly alpha. This makes those hydrogens even more acidic, which allows us to use less potent bases to form nucleophiles, which we then use in synthesis. Reactions we're going to study in this chapter include enols and enolates and condensations, and that the methodology there are aldols, Claisens, and Diekmann reactions. And then when we get to the doubly alpha hydrogens, we'll have acetoacetic ester synthesis, malonic ester synthesis, and we'll finish up the chapter with various reactions which are termed Michael reactions, and finally Robinson and Mannich reactions. As a quick review, you should remember that we have certain organic bases like sodium hydroxide, sodium ethoxide, and very important to this chapter is lithium diisopropylamide. And it's really important because it's a very strong base and not very nucleophilic, as the two isopropyl groups on the nitrogen are very bulky, create steric hindrance, and thus the nitrogen of LDA is not very nucleophilic, but it is a very potent base. And this will allow us to deprotonate efficiently these mildly acidic alpha carbonyl compounds. Also in the chapter, as I previously said, we're going to cover what's called alpha halogenation. And I was going to start the lecture there because that's what we'll be doing in our next laboratory experiment, which should be sometime in April, we hope. Stay tuned for that. But that will involve adding a halogen on the carbon next to, aka alpha 2, a carbonyl. And as we previously know, those halogens can be useful in synthesis. Good morning, Antoine. How do you do?
Good morning.
I am recording.
Oh,
You're on my YouTube channel. You got to walk in front of the camera.
Oh, okay. I'm sorry. I was just coming through. They have us checking and everything to make sure everything all right.
We're good?
Oh yes, I'm still finna going out here and we finna head to the next business.
You don't want to be on YouTube?
Oh man, no. You know, I try not to stay.
Come on, Antoine. You've been here before.
They already say the camera put on pounds, and I got enough regularly.
You too. To exemplify what we're going to do with this chemistry, we're going to start with acetaldehyde, and recall that we should be able to apply our mechanisms to what's called tautomerization between the aldehyde and the enol form. So I'll give you 5 seconds to review your mechanisms and describe how that happens. Also known as the 1,3 proton shift, you really only need 3 electron movements to get from aldehyde to enol. And to emphasize that these are tautomers, the ratio of these, which are in equilibrium with each other, is largely tilted towards the enol. So we could change our arrows like that. Also, to set up for what's coming later in the chapter, if we use a base like sodium ethoxide instead of tautomerization, we can actually remove the proton, forming what's called an enolate. Both of these systems, the enol and the enolate, have their place in synthesis. Enols more if you're using acidic conditions, and enolates would be in base. So to review, we have acetaldehyde and it's enol, and acetaldehyde, it's enol, and what's called its enolate. And as usual, we can practice and do the same thing with a ketone. So there would be acetone, and in a bottle of acetone, there's a certain amount of its enol, and the amount would be roughly about 1%. And if we were to use a base on acetone, we could form an enolate. So whether it's an aldehyde or a ketone, the resulting tautomeric compound is called an enol, and the resulting deprotonated species is an enolate. The ratio, again, is about 1% enol and 99% the original aldehyde or ketone. The pKa values for these are somewhere in the range of 20. So they're not very acidic, so you would need a pretty potent base like ethoxide to get any amount of enolate formed, and you would still have a large amount of the original ketone or aldehyde. So a lot of these reactions in this chapter, we're either going to have to go to a stronger base to fully make our enolate, or just deal with the equilibrium conditions and use trickery to get the synthesis done we need to. Where we go next is how can an enol condense with itself to make a beta hydroxyaldehyde or ketone. These are commonly called aldol reactions from the composite of aldehyde and alcohol. But bear in mind, it could just as easily be a ketone and an alcohol. But I've never heard of the synthesis ketol. At any rate, as usual, two things to be concerned of is the starting material and, first off, the overall product, which in this case is a beta hydroxyaldehyde. So obviously, looking at that, it is hoped that you see that the starting material is a 2-carbon aldehyde and the product is a 4-carbon beta hydroxyaldehyde. So when we use the word beta, it's the proximity away from the aldehyde carbon that we're talking about. And if we're going to show how this made, we're talking about the mechanism. And the first step of any mechanism is to realize whether you're doing this in acid or base. So if we wanted to use the base catalyzed version, we would leave or draw 1 molecule of the original aldehyde and invoke a base like sodium methoxide to deprotonate the alpha hydrogen of acetaldehyde. And when we do that, we're going to form an enolate. And the enolate is a nucleophile, and from past experience you should recognize that the original aldehyde is an electrophile. So that's why these two can self-condense. Obviously, for them to self-condense, you would need to have some of each still present in your reaction. Fortunately for us, the pKa value dictates that that will be true. And then in our mechanism, it's key to realize that it's the alpha carbon of the enolate, which is the most nucleophilic species or site, and it's the carbonyl carbon of your aldehyde, which is the most electrophilic. Once you realize that those two carbons are going to be the ones to be connected, go ahead and do so with an assist from reforming the carbonyl of the enolate and attacking the electrophile with the nucleophile, and to prevent five bonds on carbon toggling up the O, as we've seen many, many times. This results in an intermediate species which has that structure. And again, the new carbon-carbon bond is shown right there. And upon workup, protonation from the solvent, water, what have you, provides the beta hydroxyaldehyde. And if conditions are such that you heat it, add acid and heat it, add base and heat it, oftentimes you can get a dehydration reaction, and this would provide what's called an alpha beta unsaturated aldehyde. And this is really facilitated because of the resulting conjugation between the ene and the al. So, note to selves, beta hydroxyaldehydes and ketones can be easily dehydrated to what are called enones or enals, depending on whether it's a ketone or aldehyde. And these enones and enals are often called alpha beta unsaturated.